Okay, we talked about first order systems and second order systems. Now we want to talk about higher order systems. In general, the performance of higher order systems are different to analyze, but special cases exist under which the system's response or a higher order system's response can be approximated as a second order system or a first order system. When does that happen? Well, when something called dominant poles exists. Consider a third order system. With this transfer function, I have 3 poles here. Therefore, this is a third order system. Poles of this system are located at -1 divided by gamma and negative xc plus minus j square root of 1 minus xc squared. So 3 poles. And based on xc and gamma, these poles can be in different places. Now, if the third pole is such that 1 over gamma is greater than 10 times absolute value of xc. So this pole, let's say 1 over gamma is negative, so let's say this pole is negative 20, okay, and this c is negative 2, okay, so our c is 2, meaning that this third pole is way to the left. These two poles are way closer to the j omega axis or the imaginary axis. Then we say that the behavior of this third order system is similar to the following second order system. Again, if I have a third order system and the location of the third pole is way to the left, that pole is so weak that we can estimate the behavior of this third order system with a second order system as if this third pole didn't exist. So if I plot the location of the poles, if this pole is way to the left, it's so weak that these two poles are the dominant poles, and I can estimate the behavior of my system with these two poles. Look at this numerical example. Plot the system's response to a unit step. Well, this is a third order system. I haven't studied how to plot response to a unit step for third order systems. But wait a second. If I find the location of the poles, I have negative 0.1 and then I have negative 10 plus minus j. So this pole, negative 0.1, is very close to the origin or to the imaginary axis. These two poles are way to the left, so these are very weak poles. Therefore, this system, which has 3 poles, behaves like a first order system, as if these 2 poles didn't exist, as if this was the only pole of the system. So this is the dominant pole, and it shows itself much stronger than these 2 poles. So if we use final value theorem to find the final value of the system, we are going to see that the final value is 1 over 101. And if we find the time constant of the system, we look at the equivalent system with the dominant pole. We see that the time constant is going to be 10. So the equivalent first order system is going to have the time constant of 10, which means that it's going to behave like this. So my third order system is going to show up or show the response as if it's a first order system, because the dominant pole was this first order or this pole. And that's how we estimate our response. So a numerical example for home. For the system with transfer function given, find the overshoot percentage of the response to a unit step input. Clearly, and the solution is given to you, so we just want to see if you can get to that point. Clearly, you should be able to estimate this third order system as a second order system. So let's see if you can do that.